everyone to the 14th ML Meta lecture. First, can I request everyone else to mute their mics so that we don't have an echo? Okay, so the Madan Lal Mehta lectures is usually an annual lecture organized by the Department of Theoretical Physics. It's an endowed lectureship. The endowment was given to us by Mrs. Rani Mehta, the late Madan Lal Mehta's wife, with the purpose of, with the intent of giving us the ability to have extremely eminent speakers come over to the Department of Theoretical Physics at TIFR, visit us and give us a lecture. Unfortunately, over the last couple of years, coming over in person has not been possible because of the pandemic. So we've moved the Madan Lal Mehta lecture series online. Let me start with a brief introduction to Madan Lal Mehta, in whose honor this lecture series is held. Madan Lal Mehta was born in a village in Rajasthan near Udaipur on the 24th of December 1932.
Actually, Rish, whatever Rishi is telling, I was doing that. So, okay.
Ajay, you're not muted. Yeah. He did his master's degree from the University of Rajasthan, graduating in 1956. He then came to the Tata Institute of Fundamental Research and spent 2 years here, from 1956 to 1958. Now, in those early days at TIFR, Homi Bhabha and several of his colleagues had the system of identifying particularly bright students and trying to send them to do their PhDs to some of the top places outside in order to create a core group of trained people in India. ML Mehta was one of these people who left TIFR in 1958 and went on to Sakale to do his PhD with Cloud Block. He received his PhD in 1961 and then moved on. Then went on to the Institute for Advanced Study at Princeton for a year. Then he moved on to Delhi University. Then went back to the US for a year's stint in Princeton University and Argonne National Laboratory. This was between 66 and 67. And then finally, in 1967, he moved to Sakale as a member of the Department of Theoretical Physics there. That's where he stayed till the end of his career. Finally, in 2005, he retired and came back to India and stayed in India after that for until he passed away on the 16th of December in 2006. Madan Lal Mehta is well known for his contributions, especially to the theory of random matrices. His major contributions include his invention and use of the orthogonal polynomial method to solve random matrices, together with his collaborator Gordon, and his collaboration with Freeman Dyson on the theory of circular ensembles. His contributions are impressive, but for many of us in my generation, we know Madan Lal Mehta best because of his fantastic textbook, Random Matrices, which several of us read in detail during our PhD. So I can attest personally that that's a fantastic book, completely lucid, completely clear, wonderful introduction to an otherwise complicated subject. Okay, as I mentioned, the Madan Lal Mehta lecture series was initiated with an endowment from Mrs. Rani Mehta. We had the first lecture in this series in 2010. Professor Bohigas gave us this lecture. And the last 5 lectures in this series have been presented by Professor Ashwin Vishwanath, a good friend from Harvard, Professor Ashok Sen, the great Indian physicist, Professor Wendy Friedman, the well-known cosmologist, Professor Edward Witten, the legendary string theorist, Professor Bert Halperin, the well-known condensed matter physicist from Harvard, and now the 14th ML Meta lecture will be presented by Savas Dimopoulos, the eminent phenomenologist and particle theorist from Stanford. One or two last organizational comments before we start the real proceedings. First, this lecture is recorded, and you're continuing on this lecture, knowing that it's recorded is your permission, is your tacit permission for agreeing to being recorded on this lecture. Second, we will save all questions to the end of the talk. Okay, so please hold your questions to the end of the talk, unless something extremely urgent comes up. Then you can send a chat message, and maybe the host will permit you to ask a very, very brief question in the middle. The questions can be asked by either raising your hand, in which case the host will unmute you and ask you to ask your question, or typing the question into the chat box, in which case the host can read out the question to Professor Dimopoulos. Okay, that's it from my end. I now hand over to Professor Srirup Raichaudhuri to introduce the speaker.
Okay, it's a real pleasure. So, Professor, to people of my generation, Professor Savas Dimopoulos certainly needs no introduction. So, this is really for the younger people in the audience, because Professor Dimopoulos is one of the most creative and influential minds in high energy physics over the last 4 decades. He completed his doctoral work in Chicago with the late Professor Nambu was his advisor. But for most of his career, he has been a faculty member at Stanford University, though he has also spent a lot of time at Harvard and at CERN. And currently, he holds the Hamamoto Family Chair Professorship at the Institute for Theoretical Physics at Stanford. He's a recipient of the Sakurai Prize and the Tomasoni Kizesi Prize. To physicists, Professor Dimopoulos has actually provided a wide range of original ideas in physics beyond the standard model. But most importantly, he has been a founding father of 2 of the most influential ideas of the past few decades, and certainly the areas in which I have spent most of my life working. The first of these was a really seminal paper in 1981 with Howard Georgi on supersymmetric SU5 grand unification. This is the paper which really launched the so-called minimal supersymmetric standard model, or MSSM. Not surprisingly, this paper has more than 3,000 citations. The second, more recent, was an equally path-breaking work. It was on large extra dimensions with Nimar Kani Hamed and George Itwali, which was written in 1998. And this created what has come to be known as the ADD model. And the first of those Ds in ADD is Professor Dimopoulos. This paper has nearly 7,000 citations. So that indicates the kind of sensation it created at the time and the importance which is continuing. However, all this science you should hear from the horse's mouth. And therefore, I now have the great pleasure of inviting Professor Savas Dimopoulos to deliver his talk. Over to you, Savas.
Thank you. Okay, thank you for this very kind introduction. It's a pleasure for me to be giving these lectures, and it's an honor. I hope in the not so distant future, I'll be able to visit you in person. As I was saying, I've never been to your institution or to India, and I would love to do that. I'm going to be talking about the state of particle physics from my own perspective. This perspective, as with most people, is fairly fluid, and sometimes, there are week-to-week variations on my attitude towards the state of particle physics. So this will reflect the way I think about the state of the field right now. Can you see the slide?
We see perfectly.
Okay, very good. So in one sense, this is a high time for particle physics. We have a complete theory called the Standard Model, which was finally completed observationally by the discovery of the Higgs boson in 2012. And it's a theory which has about 20 parameters and roughly 20 particles, in terms of which you can describe the vast majority of all the phenomena, all the experiments that have been done. In spite of this, of course, we feel that the theory is not complete. For one thing, the very presence of 20 parameters suggests that there is work to be done to understand those fundamental parameters. And the 20 particles sounds like a large number. We would like to have some more unified picture, which has fewer ingredients. However, there are also some quantitative problems that we feel beg for an explanation. And there are a few of these problems. The most outstanding ones I am listing here is can be characterized by three very small numbers. One small number is, I don't know, can you see my pointer?
Yes, we see it very well.
Okay. So one small number is the electric charge of, let's say, hydrogen, which is, of course, the same as the charge difference between the electron and the proton. And that is known to be experimentally measured to be smaller than 10 to the minus 22. So in other words, the electron and the proton charge are equal to each other over 20 with the precision of over 20 decimals. The second small number, and in fact, maybe I should mention, if this number was any bigger than, let's say, 10 to the minus 19 or so, the universe would be a very different place, because the electrical force between atoms would overwhelm gravity and matter wouldn't be able to clump. The second small number is the gauge hierarchy problem, where the ratio of the Newton constant and the Fermi constant, or the ratio of the strength of the gravitational force to the weak force, is this incredibly small number of 10 to minus 33. And the third familiar small number is the vacuum energy, or the cosmological constant problem, which is smaller than its expected value by 120 orders of magnitude. So these three problems have been driving forces for building theories, and have been the foundation of what has been driving the field of particle physics and phenomenology and model building for the last 40 years or so. Among those, the gauge hierarchy problem occupied probably the vast fraction of the effort of most particle theorists. Now, there are some highlights which are possibly success stories of theories beyond the Standard Model. One is the so-called charge quantization, which comes about if you grand unify the theory in simple groups like SU5. And this was first done in 1974. And the quantization of electric charge was shown to arise from essentially the same algebra as the quantization of angular momentum. So that was an early success of theories beyond the Standard Model that, in a sense, solved the problem that is at least, explain this number of 10 to minus 22 and in fact said that the 10 minus 22 is in fact 0. A second indication, so this success of charge quantization in grand unified theories pointed theories towards the direction of grand unification. A second success of beyond the standard model, which is again quantitative at the level of a couple of % or so, is the verification that the gauge coupling unification, as predicted in grand unified theories, which have supersymmetric particles with mass around the TeV or so, was anticipated theoretically back in '81 and experimentally observed to be the case in 1991, in the early days of LEP and SLC. So these two successes drive a lot of the motivation behind, trying further to build a complete theory based on at least these two ideas, grand unification and supersymmetry at relatively low energies. Another, I should say, another motivation for going beyond the standard model that goes without saying is, of course, the presence of dark matter, which quite likely implies physics beyond the standard model, although this is not necessarily the case. So back to the small numbers that I was talking about here. There are several ways in which we can understand small numbers, and I separate them in two broad categories. First, there is the naturalness root, and which is to the right, say, and then there is something else to the left. And to give you some examples of this, let me first give you some examples of natural explanations of small numbers. Starting with the hydrogen binding energy, the mass of the electron is about an MeV, the binding energy is about 10 electron volts. So it's 5 orders of magnitude smaller. This small number of 10 to the minus 5 can be understood dynamically in the theory of the hydrogen atom as arising. First, it has to do with the fact that space is three-dimensional, so the force lines or the Gaussian field lines get suppressed by spreading in the electric force gets suppressed by spreading inside three-dimensional space. And the other statement is that the electric charge, although it's not very small, the electric charge of an electron is about a third, and raised to the fourth power, that gives you the suppression. So this is a dynamical explanation of this small number, one of the great successes of atomic physics. Similar, the smallness of the binding energy of a deuteron can be understood similarly as essentially being a consequence of living in three dimensions. And the pi plus pi zero mass difference is another famous. It's purely pi plus and pi zero are almost the same except for electric charge. So you can compute their mass difference as being accounted by the fact that the pi plus has an electric self-energy, whereas pi zero doesn't have. And so that is a manifestation that comes about because of symmetry and some dynamics, breaking of a symmetry due to the difference between, let's say, having a charge and not having a charge. Similarly, the K bar mass difference, that's a very famous, K long, K short mass difference, very famous development that drove into the first evidence for the standard model and extra generations, comes from flavor symmetry. And the smallness of the electron mass. Now, all of these that I've listed so far are actually quantitative explanations of that you can build on the basis of symmetries and dynamics. Then there is the smallness of the electron mass. The very value of the electron mass, there is no good understanding for, but its smallness can be understood, or at least can be protected by what's called chiral symmetry. And I'll come back and say some more things about this. So these are all examples where naturalness and dynamics can explain small numbers that would otherwise be very puzzling. However, sometimes there are other reasons why small numbers come out small. For example, the Earth-Sun distance. The Earth-Sun distance is, just right within, several percent for us to exist. In other words, if it was much smaller, the Earth would be too hot. If it was much bigger, the Earth would be too cold. And so this, of course, used to be a big mystery in the old days when we thought there was only one planetary system in the universe. Now that there are many planetary systems, there is bound to be some of these planetary systems that have the right conditions for us to exist. So this is one approach that has attracted a lot of attention in the last couple of decades, called environmental selection. Another sort of more accidental occurrences is in thorium nucleus, there is some energy level, some line, which is about 7 electron volts. 7 electron volts is an extremely small energy by nuclear physics standards, where energies are of the order of 10 MeV. However, there is so many nuclei around that there's bound to be some accident, so many nuclear energy levels, there was bound to be some accidental degeneracy, and the thorium nucleus is an extreme example of this. And finally, there is the there is the statement that the angular size of the sun and the moon on the Earth are about the same. And that, I don't think there is any explanation for it. Maybe there is, and I'm not familiar, but it seems to be plain luck. So, and it's in principle possible that the small numbers that we observe either come from symmetries or any such explanation that I present here. So, the main theme of my discussion will have the main thread will be that, given everything we know today and what we have learned from the LHC, I feel that nature seems to be pointing in the multiverse direction, or the so-called, something else. In fact, by multiverse, I mean environmental selection, that the small parameters that we observe in the universe are probably attributable to the existence of many solutions, or many vacua, or many universes in the theory, and that there are selection effects that come under the name of either environmental or anthropic selection that may be at play in explaining some of the small numbers we observe. And essentially, the grand reason for this is that if these numbers were not as small as they are, we wouldn't be around. And if the theory allows many different environments, many different vacua, then we are bound to be in the one that allows us to exist. So that's the so-called environmental or anthropic selection that I'm going to also be talking about. Okay, so with that, introduction. Now I'll give you an outline of what I'm going to be talking about. First, I will review something that it will be familiar to most of you, a natural approach to the gauge hierarchy problem, and in particular supersymmetry. Then I'll talk about a different approach, environmental reasoning approach or multiverse approach to the cosmological constant problem. And then I will give an argument, again, an environmental argument, or I will naturally say that environmental arguments can be embedded in string theory, and they tend to predict a plenitude of particles, some of which may very well be light and may be observable by experiments today. And finally, if I have time, I will go over a multiverse approach to the hierarchy problem. So let me begin by the first topic, the reviewing what is quite familiar terrain, the natural approach to the gauge hierarchy problem. Okay, I can skip that. Now, so the hierarchy problem famously is the statement of why is gravity so much weaker than the weak force or any other force in nature. And in particular, the Planck scale, which measures the strength of gravity, is 16 orders of magnitude bigger than the weak scale. And furthermore, if you compute quantum corrections in the theory, then the quantum corrections tend to want to make these two scales equal. In particular, they pull up the weak scale all the way to the Planck scale. So quantum corrections would like the weak scale to be as heavy as the Planck scale. But of course, what we observe in nature is a big separation. The way you see this pull of gravity or pull of the weak scale towards the Planck scale is simply by computing corrections to the Higgs mass. The Higgs mass is what determines the weak scale. So if you compute corrections to the Higgs mass, for example, coming from the top loop, you find that the corrections scale as the cutoff of the theory, which I take here to be the Planck scale. So something has to happen in the theory to prevent this. And one possibility for a physical mechanism that can prevent this from happening, can keep the weak scale low, is best developed by analogy of a very familiar historic precedent from undergraduate electromagnetism. So if back in the 1800s, theorists were worried about what was the mass of the electron. If you compute the amount of Coulomb energy around an electron, you find that the energy scales like the fine structure constant divided by some minimum distance. Then if the theory was complete all the way to zero distance, this would give you infinite energy, but you cut it off, you cut the theory off around the cutoff or minimum distance are minimum or equivalent some maximum mass, which is we will take to be the cutoff or the Planck scale. So you would think that the electron mass is in classical theory should be very, very large. So this disturbed lots of people, Abraham and Lorentz and many others were concerned about this. And a similar concern happens, in fact, in non-relativistic quantum mechanics. If you compute the quantum corrections to the electron mass, you find again some linear divergence. some linear dependence on the cutoff, which goes like the Planck mass. So this is using old-fashioned perturbation theory in computing this diagram. However, things change a lot when you add relativity, when you go from non-relativistic to relativistic quantum mechanics. One of the reasons is when you go to relativistic quantum mechanics, you introduce a new particle automatically. You introduce the positron. And the positron, of course, couples to the photon. And in terms of old-fashioned perturbation theory diagrams, the positron also has a linearly divergent contribution. However, it is of the opposite sign, and it precisely cancels the linearly divergent contribution due to the electron and gives and leaves just a logarithmic sensitivity to the cutoff. So the change in the electron mass ends up being proportional to the mass itself and then the logarithm of the cutoff. So in relativistic quantum mechanics, there is much less of a concern about the sensitivity to short distance physics. So although you don't have an explanation for why the electron mass is so small, you have the assurance that if you start it out being small in the Lagrangian, for example, then the corrections to it will remain small. Now, a quicker way to see this, this looks like a miracle, this cancellation. In fact, the miracle arises because once you introduce relativity, there is a symmetry called chiral symmetry, which, if the electron was massless, it would leave it massless to all orders. So the fact that the electron mass correction is proportional to the mass of the electron itself is a consequence of chiral symmetry. Now, this familiar example suggested back in the early 80s that perhaps something like that may be at work also for the Higgs mass. So the Higgs is a scalar particle. If somehow the Higgs had a partner, a supersymmetric partner, and the mass of the Higgs and the mass of the supersymmetric partner were equal or approximately equal, then the chiral symmetry that protects the fermionic partner of the Higgs from getting a mass, namely relativistic quantum mechanics for psi, would also protect the mass of the Higgs. Such a symmetry was invented back in the 70s, and it's called supersymmetry. So supersymmetry is a symmetry that for every scalar assigns a fermion, and if supersymmetry is an exact symmetry, the two are exactly degenerate. If it's not an exact symmetry, then there may be small corrections, small differences in the mass of phi and psi, but that are protected to remain small. Okay, so this is the cartoon of what supersymmetry does. So it introduces for every particle a super partner that, so for leptons, there is leptons, etc. And for quarks, there is the squark. For the top quark, which is very important, there is a super partner called the stop, the super partner of the top. And then similarly for gauge particles, there are super partners. And there is, most importantly, a super partner for the Higgs, which is called the Higgsino. And the Higgsino is the stop is extremely important, a super partner of the top, because it is the particle that cancels the dominant divergence of the top loop. Okay, just like the positron canceled the divergence of the electron loop in the case of electrodynamics, So the stop cancels the dominant divergence of the top loop, and so as a result, the corrections to the Higgs mass are under control. Now, the top and the stop, as I should have said here, since we obviously haven't seen any super partners yet, so it's quite clear that supersymmetry is a broken symmetry at best if it's in nature. And if supersymmetry, the scale of supersymmetry breaking is close to the weak scale, if the scale, M-SUSY scale, a scale of supersymmetry breaking is close to the weak scale, then the mass difference between the stop, the Higgs and the Higgsino, or the stop and the top, etc., will be of the order of M-SUSY squared. And as M-SUSY went to 0, there would be, the supersymmetry would be exact, and every particle would be degenerate with its particle. The fact that we haven't seen supersymmetry suggests that this number has to be at least on the order of a TeV or so. Okay. So this, of course, opened the exciting prospect that we should see supersymmetric particles around the weak scale, and that, since the early 80s has been driving a lot of the excitement, and a lot of the design of new colliders, etc., have been aimed towards such a goal, towards the discovery of such a sector. Now, as I said, the model was proposed in the early 80s. By the early 90s, essentially as soon as LEP turned on back in 91, there was a first indication that supersymmetry may be on the right path. And this is the famous plot which shows you how the strong, weak, and electromagnetic interactions change with energy. So the vertical axis is the strength of the interaction, the horizontal is energy, log scale. In the standard model, without supersymmetric particles, the three coupling constants miss by quite a lot. They sort of converge, but in the end, they miss becoming equal. Whereas in supersymmetry, they converge to within a few percent. So in the early 90s, this created a tremendous excitement and anticipation for searches for supersymmetry throughout, LEP and the Tevatron, and of course the LHC. Of course, the state of affairs now is not as optimistic as originally thought. Here is a limit. Here, on the horizontal axis, gives you the limit on the gluino mass, the super partner of the gluon, which is a strongly interacting particle. So it can be easily, if it was there, it should be easily producible at the Large Hadron Collider. And this is the mass of the neutralino. This is most likely a good candidate for the lightest supersymmetric particle. What you see here is clearly that the gluino, which ordinarily would be expected to be around the weak scale, which is 100 GeV or so, has not been discovered up to around 2.5 TeV. So at least the colored superpartners are much heavier than the expected scale. If supersymmetry was relevant for the hierarchy problem, it could explain the weak scale. Now, for the electroweak particles, the particles that don't carry color, the situation is nowhere near as difficult. For those particles, their mass limits are that they have to be roughly heavier than, let's say, 200 GeV or so, which is not that far from the weak scale. But nevertheless, there is a strong tension between the gauge coupling unification that encouraged us to look at supersymmetry and the Large Hadron Collider, which has not discovered supersymmetric particles. So that's the state of affair of naturalness. It's a state of tension that, 10 or 15 years ago we thought would be resolved in probably in favor of supersymmetry, but this wasn't. So as you will see in the last part of my talk, this failure of supersymmetry to be observed at the Large Hadron Collider subsequently led to some other approaches for the hierarchy problem that are based on environmental reasoning. But the best way to introduce what is called the multiverse or environmental reasoning is to first review the state of the cosmological constant problem, which is arguably the most important problem in physics, since it's a failure of our ideas by 120 orders of magnitude. Our expectation and the value of the cosmological constant are 120 orders of magnitude apart. So brief overview of the cosmological constant problem. So here are the three scales that have been driving physics, particle physics for the last 40 years. There is the Planck scale, the Wick scale, and the cosmological constant scale. And they are each separated from each other by 16 orders of magnitude. So now I want to discuss, essentially, well, one of the very, very few ideas, and probably the only successful idea for possibly addressing the cosmological constant problem. And by the way, I should say that the cosmological constant, by the cosmological constant mass scale, I will take the vacuum energy that is observed today to the 1/4 power, which gives me a mass which is about 10 to the minus 3 electron volts. Okay, and this mass, as you will hear several times in the next few slides, the value of the vacuum energy is very critical for the existence and the formation of galaxies. If the vacuum energy was any bigger, much bigger than it is, then the universe, the expansion of the universe would be so rapid that galaxies couldn't clump. And galaxies are obviously important for our existence because that's where stars form. And that's, and we are reliant on the existence of stars for our existence. So this is a sort of background for the importance of this magnitude for our existence. So now what I will do is I will start introducing an argument due to Weinberg going back to 1987. So in theories with very few vacua, let's say just 2 vacua, the existence of a minimum with vacuum energy that is very small is a total accident. It looks like divine intervention. Okay, to have such a small vacuum energy. In fact, as I prefaced, this vacuum energy has to be small for galaxies to form. So the proximity of the vacuum energy to the zero of energy seems like a true act of divine intervention, and as if someone cares for our existence. Typical vacuum energy should be very different than zero. In fact, as I said, it should be of the order of 120 orders of magnitude bigger. Okay. However, and that was Weinberg's point, in theories with many vacuum, this is really many vacuum, at, you know, 10 to the in the 10 to the hundreds, then there will be all kinds of, you know, vacuum energies, and in such an environment, it is likely to find some vacuum which has very small energy. Okay, in particular, this one here is in this plot a potential vacuum whose, if its vacuum energy, if its vacuum energy is small enough, then it will allow for galaxies to form. So if there are, Weinberg's argument was that if the theory allows for enough vacuum to exist, then there is bound to be one where galaxies form. And this you can call I call it the galactic principle because of the preeminent role played by galaxies. It is normally called the anthropic principle because galaxies are our homes. And the galactic principle can act as an explanation for the smallness of the vacuum energy, as long as you have a theory which allows for many solutions, many vacuum, and as long as you have a mechanism by which these vacuum can be populated. So these vacuum are realized in nature, they can be populated. So this is the analogy here. Now, this obviously, this is an extremely controversial topic, the existence of many vacua, is very controversial when it was first pointed out as it created a lot of commotion, and until the very famous KKLT paper that Sandeep was an author, there was no real foundation for how you could create so many vacua that are stable, etc. So once that was established, it created a huge dichotomy in the field. Those people who think that this idea is crazy and is not real science, which is still the majority view, and those that are more sympathetic. And those that are more sympathetic point to the following historical analogy that I like to point to. In the old days, 1600, people believed that there was a single solar system. And of course, in such a solar system, it looks like divine intervention that all the parameters on the Earth are just right for us to exist. And I'm not just talking about the Earth-Sun distance, which is a crucial ingredient. I'm talking about things like the chemical composition of the Earth, etc., and the conditions of the Earth that allowed for life to evolve. Okay, so it looked like an amazing, it was put together with very high precision. In 1600, well, actually, this goes back to some of the ancients also believed, like Aristarchus believed, that there were many solar systems. But in 1600, someone called Giordano Bruno advocated that there are many solar systems, and that we are not that important, we are not that central in the grand scheme of things, and this idea of many solar systems, first of all, looked also very crazy to the vast majority of people, and in fact, it was somewhat controversial also in high positions, for some people in high positions, such as the church. And that led to Giordano Bruno being burned at the stake in early 1600. So this is a warning, and that's may account for why many young people are not working on this field. It's very controversial, and people get fired for working on controversial ideas, but it's pretty daring if you read what Giordano Bruno says. Essentially, it is, his own way of talking about the multi-solar system, whose analog, of course, today is what is called the multiverse. That we are not that special. That the universe that we live in is not the only universe. In fact, there are many, many universes, and we are even less special than we thought we are. Now, even just the hypothesis of the existence of many solar systems changes drastically the way we think about what are important problems in physics. Okay, so for example, for many solar systems, when people thought that there was one solar system, one of the outstanding problems was how do you explain the distances of the various planets from the sun or from each other? Okay, so that was an outstanding fundamental problem. It was like the parameters. It's like the quark masses or lepton masses today. Understanding the distances of the various things was a fundamental entity, that problem. Now, clearly, there are not that many physicists today that are working on explaining the Earth-Sun distance or any such thing. All of these things are thought to be just accidents, historical accidents, and there is, 10 to the 22 solar systems, so all kinds of things can happen. So that's one way. So it changes the very questions we ask about physics. Even just the hypothesis of having plenty of solar systems without even observing them changes the questions that we ask of nature. And of course, more concretely, it points to environmental selection. If there are many environments, then there can be several accidental occurrences, and the environments which have all the happy accidents that allow for us to exist or for observers to exist are the ones that are automatically favored. So this suggests, now I will go a little rapidly, the analogy is quite clear. Today we believe that there is a single universe, and the fact that the vacuum energy is small enough to allow for galaxies seems like a divine intervention. If you have many, many universes, that divine intervention becomes just environmental selection. And that's the analogy that I want to build on with from the rest of this section. So this is again the same things I was saying before. The solar system is analog of the universe. Planetary distances become things like the parameters of the theory, the vacuum energy, for example, or the quark mass, the electron mass, the electric charge of the electron. All of these parameters that we think are sacred parameters, if there is one universe, are potential candidates for environmental selection, for anthropic selection. If you change too much the charge of the electron, atoms stop to exist. So that's a fair question to ask. So now can I use this argument to at least constrain the charge of the electric charge of the electron, etc. So the universe, instead of having one universe with many solar systems, now we have one multiverse with many universes. And then the telescope, which was the ultimate way in which we actually observe the rest of the universe, and post 1600, is replaced by something. And one possibility that I want to discuss a bit here is that potentially experiments collider experiments, as well as precision searches, may play the role of the telescope and discover evidence for new other universes. Okay, so let me now take a pause from the cosmological constant problem and give arguments. This is a sort of, very intuitive cartoon version of arguments for why string theory may allow for many vacua, and how those same features of string theory that allow for many universes, for many vacua, also may give rise to many particles, some of which may be light, and how tabletop experiments can look for these particles. Okay, so I move to that. And the many universes of string theory can be attributed to the fact that in string theory there is extra dimensions. So here, this horizontal dark plane represents, let's say, our ordinary three-dimensional space. In string theory, there are extra dimensions that go vertically. And these extra dimensions, of course, we know they are small. So they are compact, and they can be, the compactification manifold can be a sphere, or it can be topologically more complex. It can be a donut, or a pretzel, or a multi-hole, very complicated Calabi-Yau manifold, etc. So all of these are possibilities. And as you can see from this picture, you have 6 extra dimensions, you have complex topology, you have different sizes of each, of each feature on this compactified manifold. So there is an enormous number of possibility for this. And so now each one of these possibilities, the topology and the details of this compactification, play a role in nature. They, for example, determine the types of particles that the theory has. It determines the magnitude of the various coupling constants of the theory. So the laws of nature depend on the shape and, of course, of the extra dimension, and as well as the size of the extra dimension. So each one of these different compactification gives you a different solution, a different manifold. The completely different physical theory. Many of these universes don't have electrons. They don't look like anything that we are accustomed. So now, what I want to argue is that the complexity of these extra dimensions implies plenitude of universes. That implies plenitude of universes also implies plenitude of particles of different a discovery of such particles can be direct evidence for the multiverse. Now, to show you, so I want to tell you now how this is just a toy example of how such particles can arise from topology. And the toy example involves the agaron of bomb effect. So you take a solenoid, and so here is a solenoid. Outside there is, no field and no force. let me turn, in fact, the solenoid 180 degrees. So the solenoid is out of the page now. So there is a force-free and field-free region outside the solenoid. And of course, if you take an electron around the loop, you get a phase shift. Okay. Now, so this is a topologically non-trivial configuration. And of course, to create this topological non-trivial configuration in our 3 dimensions, you need energy, which is stored inside the solenoid, where, let's say, all the B field is. However, if you are in a topologically non-trivial space, you can remove the central region. So you have a state which has topology but has no energy. Okay. And so this is a cartoon of how you may get massless states, topologically non-trivial light states in theory. And of course, this phenomenon that here can happen inside the extra dimensions, and such phenomenon can give rise to massless particles from in theories with extra dimensions in general, and string theory in particular. Now, such particles, let me go back, can get mass by what are called non-perturbative processes. And these masses depend typically on these are exponentially dependent on the volumes of some of a manifold, of an extra dimensional submanifold. Okay. Now here, what you don't have to read this. This is a bit too busy a slide. What I'm saying in words in this slide is the following. If you believe that the QCD axion is a solution to the strong CP problem, in order for the QCD to be for the axion to be a good solution to the strong CP problem, the corrections that it gets from stringy effects to its potential must be very small. And in particular, the correction that scales like the exponential of some, volume of a submanifold, the volume of the submanifold in string units has to be large. It has to be like 200. Okay, in order for this mass of the QCD axion not to perturb the solution of the strong CP problem that the axion is supposed to solve. The reason for this is the QCD axion gets a mass predominantly from QCD effects. In order for these QCD effects to dominate over the stringy effects, the compactification volume here has to be large in string units. So this argument suggests that the compactification that suggests large volume compactifications as being preferred, at least in theories where the QCD, the strong CP problem is solved by the axion. So once you accept this possibility for the axion, then once you accept this evidence for large volume compactification for the QCD axion, then it is not a big additional step to think that there are many other light states that get masses from non-perturbative effects that are also light. Maybe their mass, instead of being suppressed by e to the minus s, is suppressed by e to the minus 2s, or by e to the minus half s, etc. But you expect exponentially small masses for several other particles. In any case, independent of this argument, there is a plethora of particles, and if you have large volume compactifications, they should be light, and many of them may be light and may be discoverable. And experimentally. So this can be spin 0, spin 1, and there is also other fields that may determine the size and the shape of the extra dimensions. And of course, also the higher dimensional gravitons that if you have large volume compactification. So string theory gives you the possibility of many new particles. If we are lucky and at least a few of them are light, we can look for them. They have a plethora of effects that have been studied a lot over the last decade or 15 years. They can mediate new forces, they have astrophysical signatures, and they are also good dark matter candidates. And here I have, I'll go over this rapidly. I mean, examples of experiments that are looking for these are, this is the famous ADMX experiment where you have a strong B field and axions turn into photons and you look for the photons. There are spin precession experiments. The axion essentially can couple like a B field to a spin and cause it to precess. There is, if you have dark photons, the dark photon, and you have a shielded region where no ordinary photons can penetrate. A dark photon can nevertheless penetrate it and convert into an ordinary photon. So all of these are existing experiments. They are chosen carefully, and also there are experiments. If you have moduli, this is a very interesting case. I should explain. There are some potentially light fields that are called moduli that whose numerical value determines things like the fine structure constant or the electron mass, etc. So if you have, if one of these moduli is the dark matter, then because these moduli oscillate in time, just like ordinary scalar fields, and the frequency is about their mass, this means that the fundamental constants will oscillate in time, and that can cause all kinds of interesting effects. It can, if the fine structure constant oscillates, for example, then the Bohr radius oscillates. So it breathes in and out. The Bohr radius oscillates in time, and then if the Bohr radius oscillates, then a solid oscillates. Breathes, and that can be looked for by detectors that also look for gravitational waves. And also, if the energy levels of atoms and nuclei oscillate in time, then atomic clocks made out of different species will get out of tune, and people are looking for, for how long atomic clocks remain synchronous once they start out that way, and etc. So there is a lot of interesting searches for such light particles, especially if they're the dark matter. There is one particular phenomenon which is pretty spectacular, where you look for dark, you can look for particles without any gravitational signature, without even them being present in the universe as dark matter. So, which is called superradiance. If you have a light boson whose Compton wavelength is of the order of the size of that black hole, it doesn't have to be exactly equal to the size of the black hole. It can be comparable. So if you have such a black hole and it's rapidly rotating, then by a phenomenon called superradiance, the rotating black hole can transfer its angular momentum to these, bosonic particles, and you form a cloud and spin the black hole down. So the rapidly spinning black hole loses its spin, and it creates a big cloud, like a hydrogenic atom type cloud, but the hydrogen atom, the electrons are bosons. So you have humongous occupation numbers around this black hole. And and that of course causes, that has signatures from black holes that include gravitational emission of gravitational waves, spin down of black holes, etc. That this has been the subject of active research for the last decade or so. Okay, so this is just a summary that that this essentially the point I want to emphasize is that this plenitude of compactifications of string theory can give rise to very rich phenomena, and that are attributable to the same complexity of topology can give rise to a complexity of the particle spectrum. And if some of these particles are light, as they can be in large volume compactifications, there can be all kinds of light states to look for. And people are already looking, especially in the context of some of these states being the dark matter. Now, let me see what time it is to see how. Okay, so I'm out of time, so I will go. Okay, I'll try to limit myself to just 5 minutes, if that's okay.
That's perfectly fine.
Yeah, and so I'll just very briefly tell you about, a multiverse approach to the hierarchy problem, which is a little strange. And was there a question by Sandeep? Okay, so I'll go back now to the multiverse approach to the hierarchy problem, and I'll just give you the basic. So the question is, if we adopt this multiverse or this environmental approach to the multiverse problem, how do we address the hierarchy of the weak scale? And for this, there is a very interesting paper that predates going back to 1997, arguing, which asked itself the question: is the weak scale anthropic? And so they found some very nice argument for why the weak scale may be anthropic, which goes as follows: 80 GeV is the value of the weak scale, as is roughly observed, the W boson mass. Now, and then the question is, what goes wrong if the weak scale is much below or much above? Okay, so for example, if the Higgs mass was positive and large, you would expect the vacuum expectation value to be 0 of the Higgs boson, and the weak scale would be 0. Or if the converse, if the weak scale was large and negative, you would expect the W boson mass to be much heavier. So what goes wrong as the W mass goes to 0 or as the W mass goes to infinity? So that's the question they asked. And they found out some very interesting physics. So as the W mass, and the key point to keep in mind is that the quark masses are also proportional to the W boson mass. So in particular, the up mass and the down quark mass is proportional to the W boson mass. So, and the other thing to keep in mind, which is very familiar, is that a proton made out of 2 up quarks and 1 down, and the neutron is made out of 2 down quarks and 1 up. And of course, the down quark is heavier than the up quark. So we're just armed with these basic facts, you can give argument that as the weak scale becomes smaller and smaller, then instead of then what happens is that the neutron proton mass difference starts decreasing. So normally the neutron is heavier than the proton, but as the W boson mass, as the weak scale goes down, the down quark mass becomes smaller and smaller, and eventually you reach a point where the proton becomes heavier than the neutron. So around, let's say, 20, 30 GeV, the proton becomes heavier than the neutron, and so the proton now can decay to a neutron, and there is no hydrogen anymore. So you have a universe without hydrogen if the weak scale is below 20 GeV. And well, that doesn't seem good for at least chemistry of life and biology, etc., as we understand it. And conversely, as the W boson mass becomes heavier, the mass of the neutron becomes significantly heavier than the proton. So eventually, when the weak scale becomes above 400 GeV, all of the neutrons in heavy nuclei, remember, neutrons only exist for any length of time inside heavy nuclei because of binding effects, and free neutrons decay in 10 minutes. So as the neutron becomes heavier and heavier, then eventually the mass difference between neutron and proton becomes so large it overcomes binding effects, and the neutrons just decay, and there is no heavy nuclei anymore. And that also is, this means biology is very different. You lose essentially all heavy nuclei, and in fact, if the weak scale becomes above 80,000 or 80 TeV, then the lightest baryon is neither the neutron nor the proton. It is a delta plus plus. It's made out of 3 up quarks. Because the up quarks are much lighter than the down quarks as the weak scale becomes higher and higher. So this is the lightest baryon, which is a weird universe. This is like a helium nucleus, doubly charged nucleus, and you can have electrons around it, but that's about it as far as to what happens. So you'll have a helium universe, which is extremely, anyway, it's very inert. It's a noble, anyway, so it's a very inert universe. Not much interesting can happen. So these are the types of arguments that Donahue, Barr et al. Entertained very early. This is one of the papers, in fact, that caught my eye from the day it came out as a preprint. I became a big fan of it, but I wasn't doing anything about it for decades. And well, not quite that long, but so they use this argument to argue that perhaps if you incorporate the atomic principle that atoms must exist and you must have both hydrogen and other and heavy atoms, etc., that perhaps you could use this to, of course, you don't fix it very precisely, but within a couple of orders of magnitude or 1 order of magnitude, you can argue that the weak scale can't be very different than what it is. Okay. So now the way unfortunately, I don't really have time to explain split supersymmetry. I'll just tell you it's a theory which was motivated by this, was proposed in 2004, and it was motivated. And the picture there is just rapid, the phenomenology of it is that the fermionic superpartners, that the scalar superpartners are heavy, they are above 10 TeV, and that is, if they are at 10 TeV or maybe up to 30 TeV, you can still get successful things like gauge coupling unification. But the fermions of the supersymmetric standard model are light. And that can be enforced by symmetry because fermions are protected by chiral symmetry. So the particles that are unprotected are heavy, the scalar superparticles, but the fermions, the superpartners that are protected because they are fermions, they are light. And it has, These two ingredients preserve the gauge coupling unification success and the fact that supersymmetric standard model has natural supersymmetric partners, which turn out to be fermions. And the atomic principle, the scale of the weak interactions is determined by the atomic principle, so the mass. And in this theory, unification of gauge couplings works pretty much the same as if the scalar masses here are around not much heavier than 10 TeV, then the convergence of the three coupling constant is not an accident, that it is calculable, and it works as well as ordinary. And it has interesting phenomenological consequences I don't have time to explain. The gluinos are long-lived because the quarks through which the gluinos decay are heavy. It turns out that the higxinos and the winos are also, the winos and the higxinos are long-lived, and they have calculable small mass differences. And let me skip that. There are several predictions of this theory that are analogous to gauge coupling unification. Quartic couplings and Yukawa couplings are related by supersymmetry, so you have unification of these couplings. And let me skip that. So here is a summary of the signatures that I didn't have time to. This is the message to carry out of this is that there are experimental consequences of this theory of split supersymmetry, which is motivated by the atomic principle. And you have long-lived particles like gluinos, winos, and higxinos that give you tracks, particle tracks in detectors. And there is unification of Yukawa couplings and quartic couplings. Okay, so now I just want to summarize. So, what evidence do we have for the multiverse to date? Well, we don't. One evidence, probably by far the strongest bit of evidence, is the original argument of Weinberg that perhaps it is the only known way to address the cosmological constant problem, and quantitatively, it actually predicted the value of the cosmological constant to an order of magnitude, which is quite a success, given that there is 120 order of magnitude to play with. That Weinberg's prediction predated by a decade the observed value to within a factor of 10. And perhaps a second bit of evidence for the multiverse is the fact that LHC hasn't found anything, and we know that the electroweak scale is already fine-tuned to at least a part in 100, more like a part in 1,000. So there is a tension there with symmetry ideas. So these two, especially the first, are quite serious arguments that are that may point in the multiverse direction. Now, what could constitute additional evidence, in the future? Okay, so here it's a matter of different theories will tell you different things. For example, I feel that if there is a large number of light states, like all light axionic state and light photonic states, and particles like moduli where there is time variation of fundamental constants that is observed. If you have enough observation of these of such signatures, a combination of these things, I think that will start being quite a strong indication. You will have to see quite a few to convince many people. It would take only 2 or 3 such things. In fact, 2 would be enough of these light states to convince me. It would take other, 6 of these things to convince. But there is potentiality if there are such light states causing all these phenomena like time variation of fundamental constants, etc. And I think you'll build a case. And the other thing that I didn't have much time to discuss is the observation of something like split supersymmetry at the high energy collider. That could be additional evidence. So what's an optimistic scenario for the sort of not too distant future of our field? Well, first of all, an optimistic scenario optimistic scenario for new physics, for physics beyond the standard model. Well, one is there is some anomalies. There are several anomalies in G-2, B physics, etc. And maybe some of them will get confirmed. And what is now 3 sigma may become 5 sigma or more in the not too distant future. And if there is in fact more than one and they get a correlated elegant explanation, then that could be. And the other thing is, what I was just saying before, if you have a small scale experiment or astrophysical observation suggesting the presence of new light states or time variation of fundamental constants, etc., that would be additional indication for new physics. It's also possible that high luminosity LHC may make a discovery. Now it's not easy to be ultra optimistic because the high luminosity LHC will be at the same energy as the LHC, so one has to rely on a signature that think of signatures that have not given any evidence today, but with enough high luminosity, they'll give 5 sigma. So it's not impossible. There are sort of niche signatures that would not have given any evidence now, but so that's the state of high luminosity. A very optimistic scenario would be if a very wealthy person decided to finance a super collider. That would really accelerate the time scale. There are people who could afford several super colliders. That's not usually their the highest priority in life, but they're more interested in space than in esoteric, subnuclear phenomena. But that would definitely push the field, and even then it would probably take at least a decade and a half. Even if tomorrow we have a commitment like that, it would still take maybe 1.5 to 2 decades to actually build something. Let's say at the scale of 50 TeV or so. And another thing that is somewhat of a controversial thing is magnet technology development. If there was some significant magnet technology development that could convince CERN to prioritize building a 30 TeV collider in the present tunnel, that is something that could give a significant energy boost within a decade. And some people feel that such magnet development is already here or is about to come, and etc. But such a thing, I think the chance of discovering new physics with even a modest energy upgrade of a factor of 2 for the LHC would be significant. And I feel significantly more than the high luminosity version, but of course they are somewhat different improvements. So I feel that far from being difficult to test, the multiverse ideas contains the seeds of potentially several new discoveries that are different, and now different than the normal. They are not focused on colliders. They are searches that can be done by using small scale experiments and the high precision frontier. So we are looking forward to the next decade to see what nature gives us. Thank you.
Thank you so much for a very stimulating and thought-provoking talk, Savas. I request him to chair the question answer session.
Okay.
Yeah.
So I guess raise hands. So we have one question from Sandeep, and please raise hand if you have that. Gagan, come next. Okay. So Sandeep, please go.
Okay, thank you. First of all, Savas, thank you for a really brilliant talk, and just it's always humbling to hear you with just the breadth and depth of your understanding. So thank you very, very much.
Thank you.
I've got a question coming back to something you've talked about quite a lot, but I wanted to ask you more about the possibility of small scale experiments which could test for, the plentitude of particles, as you were mentioning, axion-like, if I can use the word. But also, I'll just put a little bit of context here, if you don't mind, for a minute, which is that, okay, first of all, just is there also a connect vis-a-vis where we stand in our searches for dark matter? Because my understanding is, but please correct me, that also the sort of standard WIMP scenario is also increasingly sort of being ruled out by conventional experiments to some extent. And perhaps that suggests that we should look at, say, axion-like particles, which anyway, as you have said, are well motivated from other considerations. So that is what I wanted to ask, but allow me to put it in a bit of a context. And many of my particle physics colleagues are here. I hope I don't irritate them. But, we had really on the anvil a very excellent experiment for neutrinos in India called the Indian Neutrino Observatory. But it has really, very unfortunately, due to non-scientific reasons, run into difficulty. And in a sense, I feel it's a window of opportunity for us to step back and ask, can we do something else which can probe important physics, both vis-a-vis, say, the multiverse or complicated compactifications, dark matter, and whether we can do it on a scale, which doesn't involve a CERN type budget. And that's why I find, your ideas very interesting. And if you could comment on it, perhaps maybe our community can engage with you a little bit more to see the possibility of such a small scale experiment going forward in India. Sorry, please.
Yes, absolutely. Yeah. So first of all, 3 points there. As far as the small scale experiments, there are too many to discuss in one answer. There is, and in fact, many of these things are pursued now. It's a happy situation where, for several decades, small scale, the so-called precision frontier has been advancing at a very good rate. In fact, if you look at just the number of Nobel Prizes for, let's say, atomic physics, atomic molecular optical physics, etc., it's, I think justifiably they have a lion's share of recognition because they've done miracles. They've been able to measure ultra precisely things that we wouldn't even have dreamt of. So I think there is many possibilities. I mean, I sort of showed, a few pictures for some of them, but there are many more. One, for example, is looking for deviations for small-scale gravity in, down to distances of the order of, let's say, 10 microns or below. But if you think about 10 microns, this is smaller than the width of human hair. So the fact that we can now test forces of one type's gravity in 30 microns this is sort of gives you an idea of what can be done. But there is atom interferometric experiments to look for new physics, new forces, testing equivalence principle. Now atom interferometry has tested equivalence principle in an experiment out here at Stanford to 12 decimals. The world record is now 13 decimals, so they're marching in that direction. So there is tons of these things, and I agree with you. It's one way to do fundamental physics on a very humane scale where you don't need thousands of people working for decades with 10 billion billion per year budgets, and so there is really too many of these things. I mean, one I just rapidly mentioned, looking if there is time variation in fine structure constant, things should jitter. So you go and look for vibrations, or the typical cost. I don't know of what interest this is. I mean, one can ask how much do they cost. I think it's fair to say the total cost of a small scale experiment. I know friends of mine that live with let's say $150,000 per year funding, and they do such experiments. So the scale is quite tolerable by particle physics standards. These are breadcrumbs. So I think in principle one can have very respectable experiments. Let's say a 5-year experiment at $200,000 per year would be, $1 million in 5 years could really search for new physics in some yet unexplored region of parameter space. And that would educate, a handful of students and handful of postdocs, a couple of faculty. So it's a relatively small humane group, and I'm pulling these numbers because I see them all around me, and proposals, etc. So this is the scale we're talking about. So I think it's a great opportunity. In fact, it's interesting. When I give a similar talk in Greece, they were joking to me and saying, "My God, even Greece now can do fundamental experimental physics, small country." And so I think that's an excellent point. Your point on WIMPs is very well taken. Indeed, as far as looking for WIMPs, there is a plot that I don't have, which shows the cross section. When WIMPs, in the early 80s were originally proposed, and now the cross section has gone down by 10 orders of magnitude. So we really made tremendous progress in the last 40 years in looking for WIMPs, and we haven't found them yet. And now it's at the point where it's difficult to have a model which is both natural. The WIMPs are not ultra heavy, much heavier than the weak scale. And so there are a few models which have accidental cancellations that can account for why we haven't seen these WIMPs in these dark matter search experiments. So the WIMP parameter space is under tremendous pressure. There is some sliver below which we'll have problems with neutrino background, so we can't really go below there. So yeah, as for the India Neutrino Observatory, I really don't know enough to comment. I would have to look at it more before I can comment. Yeah.
No, thank you very much, Savas. That's very
well. Thank you, Sandeep.
Response. Thank you.
Thank you.
Gagan, would you like to ask your question?
Yeah, can you hear me?
Of course, yes.
Okay. So, greatly appreciate your very nice talk. I just had one small question that you briefly mentioned about these flavor anomalies. Some of my theory colleague, they try to dare to club all these 3-2 and the flavor anomaly mostly by LSCB and by Barbell. And they're claiming greater than 5 sigma significance, deviation from the standard model prediction. So I wanted to understand in the light of this route you are showing that the gentleman that is moving towards the multiverse direction, how are the prediction from this multiverse direction fits in to the, let's say, if the flavor anomaly stand test of the time, how do you think about it?
Yeah, well, the thing is, so you are asking whether this multiverse picture points to preferred solutions.
Exactly. Mm-hmm.
Yeah, no, I first of all, I don't think this is, at least in my mind so far, it is almost an orthogonal direction. I haven't pursued this, of course. So there is no, there is the example that I gave you of split supersymmetry. Well, I didn't really give you, I just mentioned, is an example of how, for example, if there was, within the context of split supersymmetry, which is a very concrete model, you can make statements about things like the expected magnitude of the electric dipole moment of the neutron, for example. So there are connections with very specific models that, if you have a very specific model that is, let's say, inspired by the multiverse, then you can make very specific predictions, like in split supersymmetry. But there are very few models that are concrete and inspired by the multiverse. So I think it's what you're suggesting is a good idea, to think a bit harder and have concrete models inspired by the multiverse and start looking at these anomalies in that context. But beyond split supersymmetry, I haven't explored models. There are very few, and I haven't explored. And in fact, the last time I looked at split supersymmetry was, before 2010. It was proposed in 2004, and so I haven't tried to go back and look at its predictions in light of these anomalies, if these anomalies persist. And it may be that one should do that. That may be a very good idea you're proposing.
Thank you very much. Thank you.
Sure.
Savas, I have a question, and
please.
The question has something to do with the philosophy of Suzy. So it lies with you imported the anthropic principle in solving the crises of electroweak state, right?
Mm-hmm.
And
yes,
problem with that is what I found with, for example, the weakless universe. So in the case of the universe, you decouple the weak scale, but yet you could have matter dominance. You could have formation. The chemistry works out, physics works out. As opposed to the anthropic principle solution to the cosmological constant problems. Here the thing is that physics and chemistry can work out if you decouple the weak scale. So that's what I think would have shown. So philosophically, it seems like the so-called the cosmological constant and the electroweak scale paradigm. I mean, they are they're different in the sense that the anthropics can try to solve it, right? So the anthropic idea for weak in principle sort of as nice as in the case of cosmological constant. No? How do you see that? I mean, where
yeah, no, these are great points. So let me comment on this. Actually, one common aspect of both the anthropic solution to the hierarchy and the cosmological constant problem is the following. Before you apply an anthropic argument, you have to decide what are the parameters that you are varying. So going back to Weinberg, for example, Weinberg decided that he would only vary the vacuum energy, the cosmological constant, and see what happens, if it gets too large, etc. And similarly, the argument of Donohue-Barr et al., the atomic principle, they just decided to vary the weak scale. And both of these things may be considered too limiting. One can ask the question, even for Weinberg's anthropic argument on the cosmological constant, you can ask the question, well, what happens if you vary other things? Let's say you vary, and people have studied this question, you vary the baryon to photon ratio, or you vary, several other quantities. And it's true, the sharpness of the prediction of the cosmological constant starts becoming more diffuse. Weinberg's original argument gave him a factor of 10. In fact, he improved it after, by making it more sophisticated. But then if you start varying other things, then what used to be a factor of 10 becomes a factor of 100. Now, a factor of 100, to be a factor of 100 off on a quantity that is problematic over 120 orders of magnitude is still a big success. But it emphasizes that even for the cosmological constant, it's not, once you have to really decide what is it you are varying. And there is, similarly, of course, for the atomic principle, as you said, the weakless universe, which I should just preview for 1 minute for some of the audience that may not have heard. The weakless, the original Donohue argument says vary the weak scale, see what happens to atoms. Then, excuse me, then Ronnie Harnick and others asked the question, well, what if you change the weak scale, but change the Yukawas by a compensating way so that the quark masses, which are the product of the two, don't change? Then what happens as you vary the weak scale? And in particular, what happens as you push the weak scale towards the Planck scale? And then they found other anthropic requirements that are not as stringent as the atomic principle. So all of the anthropic arguments, you have to decide what you vary. And that's why it is not as well defined a framework as we would like it to be. If you start varying too many parameters, pretty soon you start diluting predictivity, and that. But I feel that this is an issue with both the cosmological constant and the hierarchy problem. It's not just an issue with the hierarchy problem. Yeah, and it's a problem with the fact that we don't really understand the multiverse well enough to know what is, what makes sense to vary, what actually changes within the multiverse.
Okay. Thanks a lot. I think there are questions, and we have some questions on Zoom. Nishita doesn't attend that. Shrihari,
Sure.
Amol, and then Nishita will talk about the other questions.
Okay.
Shrihari.
Hi, thanks, Twin. Can you hear me?
Yes, I can hear you.
Hi, Savas. I had a similar
Hi.
question on the landscape. So I was just wondering, is there any expectation of the size of the variation of the fine structure constant? I mean, the null experiments, not having seen it already, does it tell you anything at all about, specifics of this idea?
Yes.
Does it pose a problem, or do we have any expectations at all?
Yeah, so there are two types. First of all, the most pursued null experiments look for time variation of the fine structure constant over cosmological time scales. They look at whether it changed between, in the last 10 billion years between, let's say, Big Bang nucleosynthesis and now. So that's definitely a worthwhile thing to do as far as experiment. The time variations I was mostly talking about are periodic, and the period, the period depends on the mass of the modulus, on the mass of the particle. The period is related to the mass of the particle. So it's not, this has not been the focus for as long a time. Now, periodic variations, for example, over periods of the order of days or months or years, can be quite constrained because of the tremendous progress on atomic clocks, which are, of course, very precise. So those things have now, people started looking at them. In fact, some people at NIST that, they have some of the world's best clocks, have gone back and looked at their old data or that they took over years, and they saw how, this year's and previous years data compare, and they can infer whether, at the moment they put limits on annual variations, let's say, of fundamental constants. But this has only started a few years ago. So essentially, it involves a very developed technology to go back and reinterpret data they've been taking for the last many years at the moment. And now there is specific experiments that are being proposed and funded to look for such experiments. So the null experiments are really, constraining a specific type of dark matter, and there is a vast amount of parameter space that is out there, waiting to be explored. That is accessible by present technology. And many people are obviously interested. If you tell these people, in addition to making better clocks, you can also look and possibly discover, what's the dark matter of the universe, they will, of course, jump at the opportunity to do so, and they are doing it.
So sorry, the cosmological timescales null experiments should, in some sense, very strongly constrain this, right? Because you're looking at much longer timescales. So
no, because if the modulus varies periodical, they are orthogonal in the sense that, let's say you have a modulus that has a period of 1 second, then it sort of averages out over the long time scale.
Thank you. Yeah.
Sure. Yeah.
Yeah. Hi, Savas.
Hello.
So I had a couple of questions. So one was regarding the three scales that you talked about, the cosmological constant scale, electroweak scale and the Planck scale. And of course, as your slide suggested, the weak scale is like a geometric mean of the two. Something. Have there been theoretical attempts to explain whether a weak scale can be generated from the Planck cosmological scales?
Yes, yes. The answer is not. I don't know of any successful one. That, of course, this is a sort of, dream relation that actually played a big role, although not a fruitful one, when I started thinking about large extra dimensions in the early 90s. I was just wondering whether, this is one could reproduce this relation. Somehow, if you have extra dimensions of space, you dilute not just gravity, but you dilute the magnitude of the cosmological constant. Very vague ideas that never, amounted to anything, but they were driving forces for one of the driving forces for the large extra dimensions. Yeah, I don't know of any spectacular attempt. I mean, I can tell you things that are familiar, that the so-called WIMP miracle, for example, that for a weakly interacting particle, the weakly interacting particle annihilation cross-sections give you the right abundance in a freeze-out scenario. So, I mean, if you look at the origin of that, which is quite amazing, because in the WIMP miracle, the weak interactions per se don't, in the WIMP miracle, the weak interactions per se don't play really any role. It's just a statement that if you have massive particles annihilating, in a cosmological scenario and were thermal before, the leftover abundance, you just try to be the dark matter. So the statement that mass turns out to be the weak scale has nothing to do with the weak interaction. And in fact, it's related to this accident that the weak scale is the geometric mean of roughly of the Planck scale and the 3-degree radiation background, the temperature of the radiation. And the 3-degree radiation background is not that dissimilar to the value of the cosmological constant. They're about, close to each other in order of magnitude. So the WIMP miracle makes use of this relation, but I don't know of any fruitful ways to understand a deep connection between these three mass scales in a theoretical context. It was definitely a driving force for large extra dimensions, and I spent more time trying to do that than in the beginning to work on large extra dimensions, because I thought, my God, that will solve a big problem. And yeah, I wouldn't be surprised if there is a connection, but I would love to see. Yeah, it's a great idea.
May I ask my other question?
Yeah.
So the second one was about, one of the things that you emphasized maybe a few times in your talk is that the discovery of these new light particles, axion, like as you said, would be an evidence for a multiverse.
Yes.
So of course, there are these particles would be present in many of the theories that don't use multiverse. No, just extra dimensional theory.
Absolutely.
So in a sense, since finding evidence for theories that lie in our universe is easier, would one not say that we'll try to look for such theories rather than a multiverse?
Yeah. So let me tell you. So that's open. It's true that first of all, once you have extra dimensions, independent of whether it's string theory, if you manage to have extra dimensions without string theory, you still have to address the question of compactification of the manifold. of the extra dimensional manifold. So, and then then the question is, in so doing, unless the theory is extremely tight, so it works only for one compactification and not for any other or very few, it will have this freedom that you can compactify. The size of the dimensions can be, it's a continuous variable, can be many things, and you can have different topologies. I think once you have extra dimensions, it's hard to avoid some type of multiverse because there are many, many solutions. And in fact, multiverse is fairly generic. I'll give you a toy example. Is imagine that you have a theory with, a scalar field with two minima. So there is two minima in that case. Now take n scalar fields with two minima. Then you have 2 to the n. And pretty soon, if you allow yourself to have tens of fields, you start building up, 10 or 100. I mean, who knows? Even if you make the theory of very simple ingredients, as long as you have several scalar fields and you have, potentials with a couple of minima for each one of them, you start, and then you couple them together, you get even wealthier minima. So having a landscape of many, many local minima is not very challenging. Now, the string theory landscape it is vast, but it's not very hard to imagine that once you have extra dimensions, you open the door for many, many vacuum.
Thanks.
Yeah.
Okay, Nishita, can you hear me?
Yes, I hear you. Yeah, so I just wanted to read out the questions that we have on YouTube. So the first one is from Professor Tejinder Singh, and he asks if there is any experiment or any theoretical result that we can have that would rule out the multiverse hypothesis.
Well, this is a very difficult question to answer. If you can rule out the multiverse. Okay, so I'll tell you an interesting story regarding this. When in 1987, it was, when was it? October 19th, 1987. I was visiting University of Texas. I remember the date because the stock market had crashed that day and everybody was in panic. But anyway, I was giving seminar at the University of Texas, and so Weinberg had worked on this solution to the cosmological constant problem. And the way in which he presented his work to me, and I think it's the way in which he wrote it in his very first paper in '87, was he said, I want to exclude this anthropic principle, this anthropic reasoning. So I found a way to do it. And they said, so what's that? He said, look, if the cosmological constant turns out to be any smaller than this value, much smaller than this value, then I think I can disprove the anthropic principle. And then he presented the argument. And he knew that people were going to measure it in the future to some good precision. So he was preparing to disprove the anthropic principle so the argument being the vacuum energy typically likes to be as big as possible, in fact, should be near the Planck scale. If it's much smaller than the minimum, than the value required to have galaxies, then this means that the existence of galaxies is not an important consideration. There is something else at play, maybe a symmetry. So that was his. So there is a way in which historically we could have argued against the anthropic principle. Now it turned out that the theory worked, the history worked the other way. In fact, the number was found to agree with the upper limit that Weinberg found for the cosmological constant, which of course made it into evidence for that reason. So it's not impossible to disprove, but the one big chance we had with the cosmological constant has failed. And because it's such a big outstanding problem, 120 orders of magnitude, that sort of turned the tide in favor of the anthropic principle. I'm sure I haven't thought much more about all ways you might disprove it since then, but but there are ways in which this thing could have been disproven already and they didn't work. Yeah, that's all I had to say.
Linda, do you have anything else?
There's another question, but I think there's a question by Abhijit, which might be taken first.
Abhijit, go ahead.
Thank you.
Sure.
Yeah, I was just wondering, if we have this multiverse picture, then could there be some loss of unitarity by tunneling into the other vacua, which could be observed? Decay of probabilities.
No, you could have. I mean, if you tunnel, you'll tunnel. So you go from one minimum to another. You'll tunnel the whole universe. So that could happen, and this may well have happened in our past and may well happen in our future. Yeah.
But is there a way one could detect or test for it?
For the tunneling, it may be too late because it's the whole. Those minima represent the whole universe. So you would change the laws of nature even locally. You go to a place where there is, new universe where there is no electron. So it's not a small thing. It's just you see that everything around you change. You don't even have a chance to see it because we disappear. The stuff that we are made out of stops existing when we transition to a new vacuum. There is no electrons, there is no atoms. It's,
Okay, thank you.
Yeah, sure.
Okay, so the last question from YouTube is asking whether Calabi-Yau manifolds give specific predictions for dark matter, and whether specific vacuum energies change the topology of manifolds that result.
Yeah, first of all, see what the apology. No, I think I'm sorry I couldn't hear very well. You said Calabi-Yau manifolds, whether they do what?
Do they give any prediction for dark matter?
You see, there are too many Calabi-Yau manifolds, and so there is no universal prediction from all of them. So to get a prediction, you have to be very specific about which one of these manifolds you are dealing with. So there is no generic prediction. And the second question is, sorry, I couldn't hear very well. If you can repeat it.
Yes, I think the question is whether having different vacuum energies changes the topology of the manifold in any way. Or, yeah, I think that's the best interpretation I could make of the question. Sorry.
Yeah, I'm not so sure. I mean, a priori, the answer is not necessarily, and that's all I can say. Change you.
Okay, thank you.
Mm-hmm.
Okay, I think we ran out of questions. Savas for being so patient and answering all questions.
Oh, my pleasure. It was, it was great.
Yes.
Yeah, no, just not much more to say. Thank you so much, Savas, for a very stimulating.
Thank you for having me. It's I really enjoyed it.